Hi, everybody. I know it is 2 o'clock and we're getting ready to start, but we are missing quite a few attendees still. So we're going to give it just a few more minutes, let some more people filter in, and then we'll get started. Alrighty, hi everybody. We're going to go ahead and get started here. So we just want to say thank you for joining us today. We appreciate having you here on this web workshop for semiconductor modeling and COMSOL multiphysics. My name is Tyler Cannon, and I'm the marketing events coordinator here at COMSOL. With me today is your instructor, Ping. Ping, would you like to give yourself an introduction?
Yes, hi. Thank you, Tyler. This is Ping Chu. I'm an application engineer in COMSOL and specialize in electromagnetics simulation. I'll be happy to give you this web workshop.
Awesome. Thank you, Ping. Much appreciated. Well, before we get started, I just wanted to touch on a few things, just a few notes for the attendees. First off, this event is going to be recorded today for future distribution, so I just had to let you know that. Second, this workshop is meant to be interactive, and we want to be able to help answer as many questions as you have. That being said, if you look at your GoToWebinar drop-down menu, you'll see the questions drop-down, and that's where you can place any questions, and we'll do our best to answer those for you. And then finally, after the event, you will get an email from your sales rep with a 2-week free trial and a tutorial video on that. But with all of that being said, I'm going to turn it on over to Ping, and I hope you guys enjoy her presentation. Thank you.
Thank you, Tyler.
Absolutely.
Welcome, everyone. Welcome to this workshop. We're talking about semiconductor modeling with COMSOL Multiphysics. So agenda, first I will give a general introduction to semiconductor module. And then we're going to discuss our major physics interface in semiconductor module. It's a semiconductor, and its features you can use to set up your semiconductor simulation. And we're going to bring up some semiconductor devices examples we have in our libraries. And in the end, I'm going to give a live demo to demonstrate how to simulate gallium arsenide PN junction infrared LED. You will see from scratch to set up the geometry conditions and obtain the results. So during the talk, feel free to type questions. I will address them at the end of the workshop. So speaking of semiconductor modeling, it could include many aspects. And COMSOL Multiphysics is a perfect tool for you because we include many products to simulate different kinds of applications related with the semiconductor materials and devices and industry. For instance, in the fabrication process simulation, you can use our plasma module to simulate plasma dynamics in the process chambers. And the structural mechanics module or MAPS module can simulate thermal stress, lattice mismatch, or the packaging stress could cause from all kinds of forces, outside, external loads, or even the thermal expansion. The polymer flow module can be used to simulate non-Newtonian fluid flow during the packaging process. Speaking of a chipboard level, majorly we would recommend users to use AC/DC module to simulate a lot current density or electric field, electric potential distribution. You can obtain capacitance properties and also can couple with heat transfer to simulate the thermal effect and design the thermal management. And this workshop, we're going to focus on the semiconductor module. This module is designed for transistor level for semiconductor devices. We simulate electrostatics with carrier transportation. So semiconductor module is the same as other modules in COMSOL. It's very flexible and provide advantage tools for all kinds of semiconductor devices simulation. You can follow this structure model builder from the top to bottom. That's our workflow. And it's very transparent, accessible equations. You can look at the governing equations we solve for each physics interface or conditions. You also can look at more details in the equation view for the variables being calculated or the expression we defined in COMSOL. And also, if we don't have the theory or the conditions available, you can add your user-defined expressions or equations. And multiphysics coupling is COMSOL really good at. And so as a semiconductor module, you can couple it with other modules such as AC/DC module and heat transfer module, structure mechanics module, and so on. So semiconductor module is majorly will provide two kinds of equation-based interfaces. One is a semiconductor interface based on drift diffusion equation. It solve both equation with transportation equations to simulate or calculate or solve electron hole and hole concentrations. We also have this special density gradient formulation based on this drift diffusion equation to add quantum effects in your model instead of you solving the whole Schrödinger equation interface. So we do provide this to solve the quantum systems such as quantum wells, wire stars, and superlattice, and to obtain those band gaps. And also we support the coupling between the Schrödinger equation and the Boson equation, so you can get the electron density and potential energy distribution. So today we'll focus on this interface, drift diffusion interface features. So we do have all kinds of features for a user to add in one or multiple to match your semiconductor devices conditions. For instance, we provide majorly two types of doping profiles: analytic doping and geometric doping, to define to either predefined profiles such as geometric doping. You define the doping profile in terms of distance to the selected boundaries. And analytic doping, you can have arbitrary user-defined profiles, either uniform or in terms of space with analytical or interpolation functions. And mobility models, we have several models available. You can add them together to include such as phonon effects, impurity, carrier scattering, high field velocity saturation, and surface scattering. And you also can define your own mobility models. And generation recombination, and we have auger recombination. It's one of major non-radiative recombination, and the direct recombination as SRH trap and eclipse trap resistant recombination. So those features you can get in to represent your semiconductor conditions. We also have this impact ionization to simulate the avalanche breakdown, and a direct and indirect optical transition to simulate optical electronic device. Like today's demo, we're going to use direct optical transition to simulate LED. If the above generation or recombination not suitable for your case, you can use our user-defined one to add your effect, such as radiation effects. And the trapping, you can define the bulk, the domain trapping, or surface trapping. You also can define the trap density in the your geometry, similar doping profile. And heterogeneous junctions, you can use the default continuous quasi-Fermi levels. We also support tunneling and the WKB major leads from a thermonic emission. We also have FN tunneling that is through floating gate to semiconductor. I want to come to the example. I can mention a little bit more about that. So multiphysics coupling is one of big advantage COMSOL provide. And it could couple majorly like with our wave optics module. The way to work is use wave optics module to send in light, and those light create the field will feed to the semiconductor, and the semiconductor interface will calculate stimulated emission and absorption, spontaneous emission, and get those rate and emission rate, and along with the change in the refractive index. Those change the refractive index will feed back to the wave optics physics. Then the new updated electric field or waves propagation will be obtained and feed back to semiconductor. So this whole process is fully coupled between this wave optics and the semiconductor. So you can use this coupling to simulate all kinds of optical electronic devices. So similar to the thermal effect, the semiconductor heat loss can feed to the heat source and be solved in heat transfer physics. Heat transfer physics obtained new updated temperature distribution in your semiconductor, and those temperature can be updated in your your device. So the mobility and other semiconductor materials can be updated and feed to the heat transfer and so on. And other than that, we also support connect your semiconductor device with external electrical circuit. We call the lumped circuit elements. So we do support import your SPICE netlist or export to. And so you basically can use the external electrical circuit as a source to excite the semiconductor. A semiconductor will feed back to your electrical circuit. So electrochemistry also can couple with semiconductors, especially to simulate something like iron sensors. The electrolytes can the transport can couple with the displacement of at the surface of semiconductor. And so its structural mechanics can be used to simulate the stress effect from a semiconductor. So that's the major multiphysics coupling we support, and you can couple semiconductor with other modules. So by using those features and conditions, we can simulate all kinds of semiconductor devices, from basic p-n junction to more complicated semiconductor devices. We have a large group of MOSFET examples. It's good for you to start with. We have example to simulate MOSFET in DC source. A small signal is oscillation. You can get the capacitance. And also we support several mobility models and simulate a breakdown. And also we can simulate a p-n forward or reverse recovery. That's the transient analysis. You can couple it with electrical circuits. And this photodiode coupling with the wave optics and thermal effect coupled with the heat transfer. So we have this ion sensor field effect transistor. Basically, we couple with this the bottom is a semiconductor, the top is an electrolyte, then the coupling between them is multiphysics coupling can be done in COMSOL. So this is the example to include some quantum effect or confinement by this oxide layer on the top. You can use our density gradient formalization and solve the drift diffusion equation, but also include the quantum effect. So that will dramatically reduce the computational time. And this EEPROM example is a good example to how to see how to use tunneling. So this is the FN tunneling. We have a floating gate and tunneling to the semiconductor through the dielectric material. So you can simulate the dielectric material and the semiconductor together in the semiconductor physics interface. And so as including some trap, surface trap, you can simulate these nanowires. So let's come to the example. I will show you this demo, and you can get a little familiar how to set up a simple LED model from scratch. So LED now is the device to convert electronic energy to optical energy. And so assume our geometry is as simple as we have a gallium arsenide disk. So we have the P contact on the top, and with a smaller around 5 micrometer diameter. This top disk around 50 micrometer diameter, and we have the like 10 micrometer height, and this contact is a ring on the side. So we have a doping from the top, it's a p doping, from bottom it's n doping. It's about 2.5 micrometer from top and 7.5 micrometer from bottom, it's n doping. So this is a simple p-n junction. So we're going to use an analytic doping profile to define our doping, p-doping and n-doping. So we're going to use these optical transitions to calculate spontaneous emission. We're going to clear the stimulated emissions, so because we don't have incoming light, so that will be used to simulate electroluminescence. And one recombination we're going to use in this model is Auger recombination. It's one of non-radiative emission. So this recombination also reduced the optical emission rate. So this you will see when we have different inject current or bias voltage, we'll see the emission rate difference. So we're going to obtain the IV curve by sweeping our P contact voltage, our bias forward bias from 0 to 1.5 voltage. And the emission rate through the whole device will obtained. Okay. So this is the setup of our definition, our model. We always, when you start model, you have some write some scratch on your paper. First step design, think a little bit conditions you're gonna use, then we can start. Okay. So let's start open. Let me just open COMSOL GUI. First, this you will see this model wizard. Let's click this model wizard. It will guide us through some basic conditions we need for starting modeling. Okay, a model. So let's click model wizard. then choose dimension. So we provide a 3-dimension, 2D, 1D, 0D. Of course, that's pure global equations without depending on the space. But here, because we assume our geometry is relatively simple, it has axial symmetry, so we can use this 2D axial symmetric dimension. So we'll only model the half size of cross section. So let's choose this. Can reduce a little bit computational cost, like solving time or degree of freedom. So then we choose expand semiconductor. That's the majorly interface we provide, but today we're gonna use this semiconductor physics. Click add, then we go to study type. So we have several predefined ones. Stationary, you solve the, for instance, your source is DC, so you get the stationary finals static results. And if you have your source is time dependence variation, you can do the transient analysis by this time dependent study. We'll also have some other 3. So semiconductor equilibrium usually is used to obtain initial values for highly nonlinear problem. It's the first step, and for the solver to convergence. Usually, especially you have a high doping profiles, you can use this equilibrium first, then add the stationary or time dependent followed. But here we're going to use this semiconductor initialization first, okay? So this study type will be used to automatically create a adaptive mesh. So meshing for semiconductor is kind of important. So even we do try optimize every version to automatically match for you, but sometimes user might have to put a little more effort to have final mesh near, for instance, near the context, near the location with higher gradient of doping. So those require some user-defined mesh. But we have this study type. It could give you a solver will automatically detect a higher gradient of doping, then do a final mesh accordingly. So this might give you users a little bit easy effort, or so you can always start with the semiconductor initialization to automatically generate a mesh, then use that adaptive mesh for stationary study. I will show you that, how to do it, okay? So let's load, this is the load the basic default setting. You will check this, see this model builder, and follow the model builder. You can define parameters and design the geometry, give materials and the corresponding physics and mesh and study and results, okay? So first of all, let's start with the parameter. It's good to define some parameters such as the geometric dimensions or the conditions, voltage, current, and even the material properties. It's easier for you to organize, to check. Also, you might use for sweeping later, okay? So to save us a little bit of time, I just load a file I already saved earlier. So the parameters, not many here. Basically, we have this uncontact voltage and P contact voltage. And also we have some geometry dimension. Since keep in mind we model only half cross section geometry, so this width will be like a radius of those domain and the height, and we have the uncontact width and uncontact size, that's a ring. Then we have this P contact, the radius, and the profile. We assume we have 2.5 micrometer P doping profile, and we're going to use those parameters. We have a little fillet. You will see where we to use to avoid a sharp corner inside the semiconductor, because near those sharp corner will have dramatically high numerical errors. We want to avoid that. Okay, so after done with parameters, we come to geometry. We can change unit first. So let's change to a little small scale. That's micrometer. Okay. Then we can add, you either can add from a ribbon or you can right click it. Okay. Right click it, geometry. We choose rectangle. So we can give the parameters. We just define the width of domain, the height. It's also domain that we assume the base is the corner. So basically, this is axis axis symmetry axis. Then we have this width, this major gallium arsenide disk. And also we're gonna create like a uncontact ring on the side. So we create another rectangle. So let's give the width is we defined in parameter. We just use it directly. It's about 2.5 micrometer. Oh, it's N. So then the corner here is W underscore. That's the domain. Oh, sorry, what happened here? Okay, so domain, then that's put on the side. So we can zoom a little bit to see this is a uncontact. Also gonna create a p contact patch here. Okay, so sometimes user don't like this interior boundary. We can, since it's the whole same materials, so we can remove the interior boundary by use the union operation. Let's boolean and then choose union. Now we choose both rectangle, remove interior boundaries. So that's one. So once you remove it, you will see a little sharp corner inside. We can use the fillet to smooth it. Fillet, we can smooth this corner. Then we put the radius we defined earlier. Okay, you can smooth out a little fillet. So the last, we're gonna add a patch for the P contact. So we can use a polygon and go to right click geometry and you look for a polygon. So where we can define the two coordinates, one is 0 and z is the height of domain, it's 10 micrometer, that's the 1 point. Then we put the other one is the P contact width and same as the height. So we can build. So basically polygon we define by two coordinates, that's the boundary for P contact, okay? So this is our geometry. We're done. Once we're done, we go to the materials. You can right click materials and click add a material from library. If you have the semiconductor module, you will have our built-in 12 semiconductor materials you can use directly. If you have some materials we don't provide, you are free to define your own one, then save to your user-defined library so you can use it for future, okay? So here, assume we have gallium arsenide. So we just add it to our model. You will see it show up under materials. And we only have one domain. It's automatically added to also gallium arsenide. You will see the check mark. Those are the materials we'll use for the semiconductor physics. And you will notice mobility is constant here. If you have your own mobility, you can use some function in terms of space or we have the mobility model. If you right-click semiconductor materials model, you will see here for different effects, you can add one or multiple at the same time to include those mobilities. But here we ignore that. We assume we're not adding them. Okay, we assume we just use this constant mobility for gallium arsenide. Then we click semiconductor interface. We're going to choose the Fermi Dirac ones to include the full probability distribution. And then we move to the semiconductor material model. You will see actually this temperature is room temperature as default. If you have some other temperature, you can use here too. You also can import your temperature profile. In terms of space, you can definitely define a function here instead of a constant uniform value, because different temperature will we might affect, for example, your density of state, those different in terms of temperature. Okay, so and other properties from our materials. That's it. So you can check a little bit our default conditions. Here is axial symmetry, and insulation assumes for the outer boundaries. Once you add more conditions, some default ones will be overridden. And also zero charge, that's electrostatic boundaries. If you have electrostatic electric materials, you can use this electrostatic charge conservation to define some define material in model instead of semiconductor. Okay, so as the insulator interface, if you have those interior interface between the electric material and semiconductor, you will see this insulator interface where you actually can define some FN tunneling. Today, I will not pay too much effort here, but definitely NF tunneling usually coupled with floating gate. Okay, you can see example in our library. Find that EEPROM example and see how to use it. And the heterogeneous junction is the interior boundary condition between different semiconductor materials, and will support tunneling. And you can either use the thermomonic emission or user defined, whatever profile you have, you can import as a function too. So this is our default conditions. So let's come to add some more conditions related to our example demo. Okay, so you can right click a semiconductor and look for doping. So we're gonna have two doping. One is p doping from the top and doping from bottom. We use an liquid doping model. So we choose select our domain. The distribution will assume has a box, give the region for uniform doping. And we first choose a box here. The impurity type is p doping, acceptor doping. And we assume a little higher concentration is 10 to 18, 1 to cubic centimeter. And the next, we're gonna define this box region uniform. Okay, that will be the from the top. This is all the width and depth with 2.5 micrometers. So we can define here first the 0, then the position is the domain height minus the doping depth profile, and the width will be the whole domain width, and the height will be the h dot p. That's a p doping profile. It's about 2.5 micrometer. Now we can choose the profile Gaussian profile decay. Then maybe we'll give a little bit of decay length to 2 micrometer. Assume that's our doping profile. So you can change the name just for you to recognize what this doping is. So we can define p doping and do the same thing. Let's do right click semiconductor, add another analytic and select the domain. Then we choose distribution as a box. Then we change impurity type as undoping, and we assume the same p-n junction, same concentration, and a little different, the base is here, so 0. The width will be like the width here plus the unring width, so we put the W, the domain width plus W, uncontact width, then the height will be the domain height minus H p doping height. So it's around 7.5 micrometer. And same as decay, then we can put the same as decay profile, the Gaussian profile. So you also can change the name as like undoping. So sometimes users say, I'm not really sure, did I do correctly? So you can actually, before you compute, you can use, for example, we can add a stationary study to our model. You can right-click stationary and select get initial value. So this way will give you the profile, electron concentration and the hole concentration. So this will help you to tell if you define it correctly or you want to do it is the doping you want to define in your model. Okay, so this is the one way before you compute. It's good always check. So let me just remove this first. Let's continue with our setup. So we did a p-doping and undoping. Let's continue with our contacts. Assume we have a metal contact. Of course, we have other kind of contact for the thin insulator gate. If you have the oxide and a metal contact, we have ideal ohmic and also Schottky with barrier too. Okay, so here we assume it's just the ideal ohmic, it's a metal contact. So first, let's choose P contact boundary. Then we can define our voltage as V underscore P. Then we say do the same again, right click semiconductor, choose metal contact. Then we choose the uncontact. Then we can give the voltage. That's the parameter we defined in the parameter setting. You can go back to check a little bit our parameters. So then after doping, then we have the contact condition. The important part is the optical transition because it will simulate LED, right? In not adding this, you will not get emission rate. So we choose the optical transition is direct optical transition as default. So we select a domain, then we're gonna clear this stimulated absorption and emission because we don't have incoming light. Okay, so only simulated spontaneous emission. So this is our setting for optical transition. So the last we include this recombination, Auger recombination. Okay, click here. So you can check the Auger combination and the input requires Auger combination factors. So we go back to our materials. So you will see this is missing. We don't have it in our material library. So user need to provide your own by your own. Okay, assume we have a constant value is 10 to negative 31 with this semiconductor centimeter to 6 over a second. Okay, same as the whole factor, so we can put 10 to negative 31 and the centimeter to 6 over a second. I put the unit here. So yeah, I assume this is my materials factor. So if you have a different, you define your own in this material property level, okay? So that's it. So basically, it's our simple setup conditions. Again, recombination could have other kind possible in your device. Here we only consider one of them is auger recombination. Okay, so we can go back to take a look at our mesh. Again, COMSOL try to automatically detect where our contacts, you will see the P contact and the N contact have a little finer mesh. That's we actually optimize mesh already, but might not enough because it doesn't really recognize doping profile. So in this case, you can use semiconductor initialization. You will see it's automatically enable this adaptive mesh. So COMSOL will solve, the solver will solve, recognize the doping profile and looking for the high gradient of doping and get finer mesh in those locations. So we can compute this instead of plot the generated default plot. I just want to create the adaptive mesh. I can click compute. And you will see if it's need to have a little finer mesh, another mesh will create it under this mesh node. You will see have a little different mesh, definitely recognize doping profile and get a finer mesh correspondingly. So once you used created a better mesh, we call it adaptive mesh, you can use it for another study. Now we're gonna solve the stationary. So in this study, in the mesh node selection, we're gonna use the adapt mesh created by this the first study, semiconductor initialization. So this will again mesh, a good mesh definitely will help solver to obtain convergence. Okay, especially the highly nonlinear cases. So first of all, we choose the mesh as adaptive mesh. Then we expand the study extension. We're gonna sweep our voltage. Okay, so COMSOL always recommend when you simulate a semiconductor device or material, you always run this continuation solver. That means you not increase the voltage as large number at one step. Instead, we start with 0, then slowly increase the value to what you want to obtain. In this case, with sweeping also we can get IV curve, so it's also useful. So in order to make a little finer, sweeping values, because I know in after some value around like 1 volt will be increased dramatically our current. So I can make a little bit finer 0.24. I use log range just to help me get a little bit of finer distribution of voltage. So I can use like start from 3.6 and 0.1, then to 0.5. Log 4.5 give roughly around 1.5 volt. So I divide sweeping my voltage by this way. It's not necessary, okay? You can do from 0 to 1.5 voltage with a step, no problem. I just give a little bit of finer steps in later near the 1.5 voltage, okay? So then you can compute. During the computing, and you will see the process, solver sweeping the P contact voltage from 0 and reach to around 1.5 voltage. During the computing, let me just check our questions here. Okay. Sorry, let me just double look. So we have a question: what's different between FN tunneling and WKB tunneling. Oh yes, I briefly mentioned. So it's FN is easier to get through the experimental results, not WKB. Right. Correct. But you know, they have different. These two kind of tunnelings has different um, from different physics phenomena. The FN, you know, is a high floating gate and jumping through those dielectric material. But that is the floating gate need to be very close to the semiconductor. That means that the electric that layer is very shallow. So they just the different, and the WBKB is basically the it's the interior junction between different semiconductor materials. That's a little barrier. Yeah, depending on what fit your case, you might choose correspondingly. And you also can, you know, use your user-defined junction. Again, this junction is a hetero-junction, and FN is the junction between the electric, you know, it goes through the electric barrier. We also have some Schrödinger equations. You might simulate those better by yourself, I mean, in COMSOL, and obtain those information. That is another option you might try. Yeah, they just the different junctions condition is from different physics effect. You might want to consider what your device, you know, qualify, which conditions fit better for your case. Another question, multiphysics coupling between wave optics and semiconductor. I'm not really sure what's your question. The electric, metal, semiconductor, the electric, oh, metal, oh, you want to model metal and the electric in the multiphysics coupling, that's what you mean? That's a good question. For instance, in this example, this LED will only simulate a semiconductor. We do not really simulate metal. We just like use a boundary condition to represent metal, right? Sometimes user do want to include metal in your system. Definitely you can. The wave optics but the thing is depending the frequency. If it's pretty high, you know, most of the field actually it's only on the surface. It's not, you don't you can't simulate in wave optics. You can include it in wave optics module and simulate, but most of the field basically just near the surface is not really useful and not that much information you can get even you include metal. But if you want to couple, you know, simulated metal and semiconductor together, you definitely can do so. The thing is you would need to couple with electric current. Let me just yes, you're gonna use our under ACDC. Then we have this electric current. So you can use the electric current to simulate metal. Then the interface between the metal and the semiconductor, you can add a condition to send in those displacement field and a normal current to go through. So you can couple the semiconductor and the electric current with together to simulate metal. Okay. Also, the electric, you can add the electric materials. It's charge conservation and simulated electric with your semiconductor together. Okay. Then let's get back to our model since it's done with the computation, and let's plot some interesting variables and expressions. Then I come back to the questions. Okay. So after compute, the default plot like electron concentration, hole concentration, potential, right? So we're interested in such as IV curve, so we can add a 1D plot group and choose, make sure to study 2 solution. Then we can add a global. You can choose our expression. If you don't know the expression, you can look for here enter the terminals. It's the first terminal. It's the first one you see the index number here is sorry, here is a 1. So that's the P contact current. So you can plot it in terms of the voltage. You also can change unit if you want to change it to milliampere, ampere. Okay. So this is the IV curve. We can plot, for instance, the emission rate in the device. We can add maybe a 2D plot and make sure this is the stationary 2. Then at a surface, the emission rate you can look for again. Either you can search like emission, right? You also emission. You also can go through those semiconductor under the generation. We can use this spontaneous emission. We can click this, so and plot it in the space. And you will see for lower voltage and higher voltage, it's more localized underneath this P contact. So that's the emission rate in the whole device. Apparently, it's not uniform. To get the total emission rate, you can do integration. So to add integration, we have this coupling. It's called under the non-local coupling. You can add integration, and you can integrate the domain or boundary. Here we integrate the domain. So we select this. Then we go to study to update our solution because we didn't add those interpolation earlier. Then compute. So then you add the integration in order to update the solution. You can go to the, instead of compute again, you can just click update the solution. Then we can add another 1D plot group, then choose 2D, study 2. Then we add a global. We want to integrate this spontaneous emission in the whole domain. We're gonna use this integration coupler. We just defined it in top 1, right? Then we can integrate this whole domain. Then maybe we plot in terms of current, injection current. So you can either click here or manually type yourself. That's the current. You also can choose like a milliampere. We can plot. So since this is the integration, the whole domain take a little bit of time to go through each parameter. So since it's important to take a little bit of time, let me go through the examples, the questions. Sorry. Hello, do we need a semiconductor module? Yes, semiconductor module is required for this all semiconductor device simulation. And what's the main difference between drift diffusion and the Schrödinger equation? And what are the factors we need to look at before deciding between these 2 equations? Oh, yes. When you have those band structures and you know all those band gaps of your materials, you can, because drift diffusion is classical way and Schrödinger is quantum. Okay, so drift diffusion, we consider those electrons in the holes as carriers. They're moving, transport under like a drift. Drift is driven by the field. Okay, when you have electric field, then those electrons and holes will move. Then also the diffusion is driven by the concentration. When your electron concentration has a higher and lower, then electrons will move from higher to lower direction. So this is we call the drift diffusion equations. So that you solve this more a classical way, not a quantum way. Okay. It's we still have those band graph, but still based a little bit different physics. So that you solve a Boson a portion this is a Boson equation. But quantum the Schrödinger equation is you solve electron density and those voltage is slightly different. But for most like a device you try to simulate, you know the major material properties and those like a band gap or like energy density. You already know. You can use this semiconductor interface. Schrödinger equation is you have a special conditions, and in the quantum ball you have those barriers, but you don't know the electron density distribution. You don't know the states, density of states. You want to solve it, you need to use Schrödinger equations. Okay. I think it's time's up. I get this is the plot. You will see the total rate, and in terms of current, injection current is slowly getting linear. That if you want to plot the so-called internal quantum efficiency, you can do the for instance, if we plot some range from 5 to 21, then we plot this is the total emission rate. If the internal quantum efficiency is the ratio between the total emission rate over the carrier injection rate. So we can use like divided the charge. So this will give you the internal quantum rate. We can plot, for example, in terms of the injection current. So we can plot it. It take a little bit of time. You will see actually this efficiency will reach to start very high in the beginning, but slowly reduce and reach to a plateau. Okay. I'm sorry, I guess I don't have enough time to answer all the questions. I will try to answer you. Sorry, I have a miss. Sorry, I have missed. It's constant typo. I have a typo there. Yeah, I have quite a few questions. I will try to reply to you later through the support. Yeah, let me see. What when including discrete traps in my model, it becomes almost impossible to convergent. Oh yeah, suggest traps. Yes, that's a really good question. It's really common. When you add the traps, it is dramatically increase the nonlinearity. So we usually do is very similar to this. We always ramping. Okay, ramping is one way to find good initial values. When you have traps, you usually will solve something like, for example, I just put one trap. Okay, for instance, assume I have a trap recombination, but this is one example. If I have this, you can solve one without it. You enable this setting and disable this trap. So first of all, you want to solve your model without trap. okay? Then you do this, sweeping the voltage. Then when you get converge, you add another study. For example, you can add another study. Then in the initial value, you choose the early previous study one. So this help you to get solver to converge. So this is as our age. If you have the, for example, explicit trial, you might have several levels. You also need to sweep the density, okay? Sweep the trap density if you define some trap density here, right? It's a similar like a doping. You wanna, if you have really high doping profile in your model, you want to slowly increase doping concentration value. And if you also add this trap density in your model, you also need to slowly increasing wrapping and run this so-called continuation. Okay, that's usually the very basic tips you might will use for your convergence case. I'm sorry, I think time is up. Seems I still have quite a few questions I haven't answered, but I will address them through emails, okay? Thank you for coming, and feel free to contact us. We'll be happy to answer your questions and concerns. Okay.
Awesome. Well, thank you so much for a great presentation, Ping, and also thank you to everyone who stayed for the entire event. We hope you enjoyed what you saw today. Just as a reminder, everyone's going to receive an email within the next day or two from your sales rep with a 2-week trial from support. And then also there's going to be a recording available of today's session if you want to rewatch that as well. So like Ping said, if you have any questions, please feel free to reach out and send a request on our website, and our support team will get back to you. But other than that, I think we're about ready to wrap up. So I'm going to go ahead and exit out of this session, and I hope you all enjoy the rest of your day. Thank you so much for being here.
Bye-bye.